Welcome, friends. My name is Vijay Kumar. I'm the Dean of Penn Engineering, and I'm your host of Penn Engineering's Innovation and Impact podcast. Our podcast shares insights from some of the leading experts from around the world who bring to you the latest breakthroughs and innovations in science, technology, and medicine. Today, we're honored to sit down with Jason Cong. Dr. Cong is the Volgano Chair for Engineering Excellence at the University of California, Los Angeles. He's a professor of computer science with a joint appointment in electrical and computer engineering. A member of the National Academy for Engineering, his research focuses on customizable computing. He also works on VLSI design and quantum computing. He has co-authored more than 600 publications. He co-founded the FPGA synthesis company AutoESL, and he has received numerous honors, including the 2022 IEEE Robert N. Noyce Medal and the 2025 ACM Chuck Thacker Breakthrough in Computing Award. Thank you very much for joining us, Dr. Cong. Let's get started. Jason, your work has helped shape customizable computing. I just wonder what drew you first to this area, and why has it become so important today in the era of AI?
So to answer this question, I have to go back maybe for 20 years. At that time, there's something called the Dennard scaling, that is stopping. It used to be the case that when you scale transistors based on Moore's law, and everything also get, not only transistor gets smaller, but also get much more efficient energy-wise. But around 20 years ago, that you cannot do that anymore. You can make the transistor smaller, but you cannot make them more power efficient, so that you can see the power density increase a lot. The chip can burn. So there we have to think aggressively on energy efficiency optimization. So customized computing really was intended to bring order of magnitude better efficiency when we do computation. The idea is that you don't want to do one size fits all. You want to come up with a specialized architecture for certain workload. In our society, we get used to this concept, right? If we get sick, we go to see a doctor, we go to see a lawyer, because everyone's specialized. That specialization make that society runs more efficiently. So, but it used to be the case, we have one general purpose CPUs running all sorts of workload. You can imagine it's not very efficient. It's almost like one high school students trying to solve all the problems in the world. So this specialization allow us to go customized towards different workload. And in the AI era, when we started, it was in 2008, 2009. We submitted a proposal to the National Science Foundation. We were very fortunate we got funded by one of their largest program called Expeditions in Computing. At that time, the application area was actually medical imaging. But soon, 4 or 5 years later, deep learning was taking off. You can see it's a very big workload. You can do a lot of customization, specialization. We built probably the first FPGA accelerator for the deep learning. That acceleration at that time was AlexNet, VGGNet from Google. And these days, of course, you can see all the major industry players that have their specialized accelerator.
Mm-hmm. You mentioned Dennard scaling and Moore's law. Companies like OpenAI propose scaling laws for large language models. I wonder if you think about those and to see if they're actually realizable or not. And unlike Moore's law, which we've shown has for 5 decades has done very well.
Yeah. No, that's an excellent question. That the question is this scaling laws at the two opposite end. One is that Moore's law scaling or Dennard scaling is about the device scaling, right? How can you make the transistors smaller and smaller and more efficient? The large language model basically says, how do we make the model larger and larger, more parameters? But if you have more parameters, you don't want to overfit. So you have to feed in with more data, right? So far, the large language model scaling has working out very well. But the natural question to ask is that, do we have enough data to feed into the training of the models? If you're talking about the text tokens, probably we have used, if not all of them, most of them already. So we have to actively thinking about the other type of information. For example, a new baby that the first 6 months is all observing, right? Certainly there's a lot of images that video type of information take advantage. And now in this agentic world, the agent can have actions. You can change the world, you can observe. I know your specialty is in robotics. Robots can change the surroundings, environments, so you can keep generating new data. So I think, if you ask me, I think it's sustainable, but we have to be thinking creatively. Just train from textbook probably is not going to be enough to do that.
Yeah. Back to hardware. So I know you spent many years, your entire career, in fact, studying FPGAs, how to design them better, high-level synthesis tools. And I just wonder how these technologies have changed in the last several years, maybe the last couple of decades. And how do engineers now build modern computing systems?
Just for the benefits of some of the audience, if you do not know, FPGA stands for Field Programmable Gate Arrays. This is one type of integrated circuits you can actually design and implement in your office on your desk. Or if you don't want to own them, you can actually design them in the cloud. Amazon, for example, AWS cloud, they have FPGA cloud. You can make use of that. In fact, I teach a class, CS133 at UCLA, on parallel distributed programming. Students got to play with FPGAs in the cloud, right? So why do I like them? There's multiple things. One is that the reason it's programmable at your home desk is that the logic can be changed by writing different bit streams. So it's something you can program, and also you can reprogram. If you change your mind in the next hour, you can create different circuits. In the AI era, this is very important because the model progresses very fast. Think about we were 10 years ago, we were using something called convolutional neural networks, and very quickly people use transformers. And now everyone is using large language models. There are many layers of transformers. And I give the talk this afternoon. You can also have many variations of the large language models. So on the average, I think every 3 to 6 months, you come up with one that new models. However, if you come up with a customized circuit, we call the ASICs, application-specific integrated circuits, that takes 12 to 24 months. FPGA give you a very nice sweet point that you can change that in the order of days. That you can reprogram certainly in seconds, but you too have to do the design. High-level synthesis give you also another way to improve the productivity. Used to be the case, you have to write your circuits in a very specialized language called VHDL or Verilog. We call them RTL languages because you have to describe what do you do at every clock cycle. With high-level synthesis, now we can write a C program. You basically provide a much higher abstraction. You don't have to say what do you do every clock cycle. You just to say what do you want to accomplish. If you want to accomplish matrix multiplications of two dense matrices, just write it down. In programs, we'll compile, schedule, and do the resource allocation. And we have research going on just to further kind of enable the AI researchers to go from fast, basically model to silicon or idea to silicon. Now we can start from PyTorch models that you can go directly compile to silicons, right? So that I think fundamentally will, I think, improve the iteration speed, and you can actually also validate the experiment with a lot of new ideas.
Mm-hmm. Mm-hmm. I wonder if you could tell us a little bit about your entrepreneurial ventures. I know you helped co-found AutoESL, and that has led to synthesis tools that are now widely used. Could you comment on the impact that this has had and what you're most proud of?
Yeah, so I will say that actually the AutoESL is my second company. The first company called the A+ Design Automation. And at that time, I was totally unprepared. We have some wonderful research about how do you map Boolean networks to lookup tables? Lookup table, by the way, is a building block used in FPGAs. A lot of problems are NP higher, but this problem we show we can solve it optimally in polynomial time. Basically means it's very efficient. So a lot of industry was interested in. There's this company called Cypress Semiconductor that says, okay, can we use it? And it says, sure, here are all the source code. You can use it. Maybe you can think about how to support some of our research. And then eventually, after 2 or 3 months, they came back. They says, oh, we find this is exactly what we need. I said, why don't you use it? He said, well, if we support a $100 million, $200 million product line, we need customization, we need the bug fixes, we need the new features. Would you be willing to do that? So as you know, that in university setting, we're not set up to do that. Once paper is published, we move to the next project. So that actually, at their encouragement, we spin out the company, and then actually we work with not only Cypress, later on a few other FPGA companies that are acquired by Magma Design Automation. Now that's part of the Synopsys. So that's now our first experience. But through that exercise, I learned a lesson is that if you want the technology to generate impact, right? So you have multiple ways. One is you can make it a widely successful open source project. But then it's equally important to have a team of bright engineers that to support that over a period of time. So that's the motivation we have. At that time, I think we had some very encouraging results. For example, we can compile about 6,000 lines of a description of an MPEG encoder for image processing to 50,000 lines of that RTL code. Several companies says, can we use that? So that's where we launched the company, and then we, and this is also where kind of a star PhD students can continue to work on it and transfer the technology. That turned out to be the best way to do that. And after that, I think Xilinx made the acquisition that in 2011, they have done a wonderful job in integrating that into their entire FPGA design suite. So today there are tens of thousands of people using that. And Zhiru Zhang, Professor Zhiru Zhang at Cornell, he was my former student, also a co-founder of the company, showed me some slides. There are thousands of papers, for example, written that with high-level synthesis. We know less about the industry usage that from outside, but from understanding from my colleagues at the AMD, it's also well used.
So Jason, I know you're all about efficient computing, so I want to talk to you about power. This is one of the hot button issues. Any student you talk to says, you're working on AI? I mean, surely you got to be aware of the energy implications. And of course, the global warming discussion starts after that. And so just thinking back to what the human brain does, which uses roughly 20 watts of power. And if you do a math and you just calculate the total amount of power that all humans in North America use, that's roughly about, I would say, 7 gigawatts. You just do the population times 20 watts. On the other hand, if you look at what hyperscalers used in the US, that's about 60 gigawatts, almost 10 times more. So something doesn't compute. And I apologize for the pun on that compute. But it seems like your work points to a way that allows us to come out of this scaling law, which is going in the wrong direction. And perhaps you could comment on that.
No, power and or energy is a very real issue that of a lot of concern, and it's glad you asked that question to just bring up the awareness. I think right now there's this rush to AGI, the artificial general intelligence. People care a lot more about the capability, not so much about the efficiency. But there's a lot to be gained on the efficiency side. For example, in my talk this afternoon, where I talked about this model where you can use a hierarchical memory transformer, right? That we call the HMT. So you don't have to do a very long context attention. That you can do it selectively, but you store your information in the long-term memory, and then you recall from your long-term memory. So then you cut down the context window size dramatically from millions to tens of thousands or several thousand. So that can be a big boost. I also showed some research we're doing there. Maybe we can just don't do computation. We do table lookup. Because I don't think you and I having this conversation will keep doing matrix vector multiplication in our brain, right? So a lot of knowledge that encoded, distilled into that. So I think a large lot can be done that way, that to make it a lot more efficient. So I think that's where university can have a leading role in improving the efficiency. So any of these new models we talked about, it can bring in somewhere 5 to 10x improvement. When you compound them together, I think getting 100, 1,000x totally possible. Another dimension, of course, is to use more efficient devices, not just all GPUs. GPU is a wonderful device when you do training, but when you do inferencing is something probably will end up doing more. Is that all the time either human use that to reason or agent use that to reason. So they have a very different computing characteristics, and you can come up with customized architectures. Coming back to your first question about customized computing, right? So there we show there's a lot of opportunity. For example, using FPGAs or some of the devices that of that kind allow you to do customization a lot more efficiently. Even a GPU plus FPGA, some kind of a hybrid, we call it disaggregated inferencing, can give a several X better energy efficiency. But bring up the awareness is very important. Last quarter, I taught a class with my colleague, Professor Yizhou Sun. This is all on energy efficient inferencing on edge devices. A student get a first hand of experience of that. The Qualcomm was a big fan of our class. They donated 20-some mobile phones for us to run a large language model on that. Student has to complete some project. Once they start running on this large language model on the phone gets so hot, they have to throw it into the refrigerator, right? Some of them and the others, they have ice pack on top of the phone. One student told me, oh, my ice pack used up, they melt. He had to get the frozen wonton and put it on that to finish the experiment. So they get a first-hand experience that how much energy is consumed and how critical it is that if you are not careful, then they can burn your phone batteries in a matter of minutes, right? So this is the same thing that if you scale up at the data center level, it's very, very serious problem.
So you mentioned industry and the role of the university. I wonder if you can say more about that. So in your career, you've been very successful at choosing the right problems to solve. I think that's getting harder and harder as I would say industry's overtaken academia on so many fronts. So a two-part question: how do you decide, or how do you advise junior faculty to decide what careers to pursue? And where do you think universities are strong as compared to industry, which has just so much more resources and also so much more data and compute?
Yeah. I think university has a lot of advantages. In fact, early today, there was a junior faculty asked me very similar questions. His professor has to decide what problem to choose, right? I just gave him the example. You roll back to 30-some years ago when I wrote my first NSF, National Science Foundation proposal, was on VSI interconnect. Why is that? Because you look several years out to look at the technology roadmap, right? What's the building, basically the bottlenecks. At that time, if you follow the projection, you will find out the interconnect delay is going to be longer than the logic delays, which is sort of in the past, because you think you do an AND or add that computes the time, and then you transmit the signal from one end of the chip to another end of the chip. By the way, this is just only 1 centimeter. That you can think about that speed of light or something close to that. Why do you bother? But that becomes a bottleneck. So that transition introduced a lot of new problems. So actually, I had a multi-decade research on that. By the way, that problem is still not solved. So for example, we started with, first time we said, so if that's the problem, what's the topology should we use? What's the geometry should we use, right? If we cannot solve it in a spatial domain, can we solve it in space and time together, right? So there's a lot of new opportunities. So I will say one of mine is to look at the problem with a long-term impact. It's not going to be going away in 2 years, 5 years, maybe. Also, in that context, we started to work on 3D IC design. The student who graduated in mid 2000, she's an excellent student, but actually didn't get any offer working on 3D ICs because industry is totally ignoring that area. 10 years later, she got 3 10-year most influential paper award for that. So that's the lead time we have. Today, a lot of people are talking about the memory shortage, especially HBMs, high bandwidth memory. That's all 3D stacking of that. But think about it, we had a book on that the 3D IC design 20 years ago. So that's the lead time we have. So again, coming back is what are the fundamental limits? For example, you asked a very good question about energy efficiency. I think that problem is not going to go away, and then it's actually going to stay. And then I talk about some innovation from model, innovation from architecture, but don't overlook there's also a large dimension from devices that you could actually, I mentioned that you could have some embedded memories, back-of-the-line transistors, stack memory on logic in a 3D integration. There we show you can get 10x speed up over in decoding over modern GPUs, right? So if you think about this kind of a problems that we can be 5-10 years away ahead of industry. One advantage working at the university is that highly interdisciplinary and across that within the city block, I can talk to experts, right, from application to device to architecture to the AI models. Not any single company has that expertise, right? That how many people, for example, in OpenAI and those chip designs, although I have to say they're just setting up a group doing chip designs, right? So how many that the experts you have that looking at the emerging devices at any of these big companies, they have their strengths. There's no doubt. Tremendous amount of computing power, tremendous amount of amount of data. That's actually, if you directly compete on those problems, I think we'll lose. But there's many other problems fundamentally will have a longer term impact.
I think another advantage that universities have is really access to the talent pool. I think industry, of course, does have talent, but we can fish. We can across the world. We get the best students coming to UCLA and Penn. That's one advantage. So I asked you a bunch of questions connecting to research and development, but maybe I can ask a question from a student standpoint. So students entering in engineering, knowing that AI is dominating pretty much everything, what are the skills today that are most important? What should they be learning? And as faculty, what should we be teaching them?
So that's a excellent question that a lot of people are asking. I think several things that first, knowing how AI model works, I think it's very important. And that fundamentally we should think about in our curriculum. For example, these are very sophisticated statistical engines. That I think knowing more statics is very useful, and which I wish I took more classes on that, right? And then all these are trained through sophisticated optimization. Knowing optimization, that's important. And so basically, you don't want to be a passive user of AI technology. You want to be an active the contributor of AI technology. So, and all that said, remember these large language models, the ChatGPT or Gemini, are wonderful, but you have to write prompts. So you have to ask questions. So it's always the case that people ask the right question, like ask the stimulating questions. That's most important. So that's require we to think deep, think wide, to make the best use of these tools. And some of my colleagues wrote a book that he was a university president. He was just talking about contracts to different cultures. In one culture, that the parents ask the kids saying that, how did you do in the class? What questions did you answer? In another culture, the student come back and the parents again, how did you do in the class? What question did you ask? So these are fundamental different ways to do learning, you can say, but from day one, you want them to ask the right question.
And maybe these LLMs do encourage you to ask the right questions.
Yeah.
Otherwise, they're useless.
That's right. Yeah.
Yeah. Jason, thank you so much for sharing your insights, your vision, and your time with us today. Um, I know you agree with me when I say the future of computing is bright, a lot of opportunities, and we appreciate your coming here and sharing your insights on computer architecture. Thank you, and congratulations once again on the Pender Award.
Yeah. Thank you very much, and deeply honored for this recognition from Penn Engineering.
For our listeners, please subscribe to Penn Engineering's Innovation and Impact podcast series on your favorite podcast platform and watch a video of this recording on Penn Engineering's YouTube channel. We'll see you next time.